chemical equilibrium. We'll be solving level 1 gaseous equilibrium problems. These are the easiest level equilibrium problems that you can solve. In order to solve equilibrium problems, you must realize that equilibrium is defined as when the rate of a forward reaction equals the rate of a reverse reaction. So you have to realize that reactions are reversible. Not only can reactants form products, but under the right conditions, products can reform reactants. And if they're doing so at the same rate, this will be defined as chemical equilibrium. How do you know when you look at a balanced chemical equation that it can reach equilibrium? Well, it's going to be symbolized, instead of with one arrow, you're going to symbolize it with double arrows. An arrow pointing to the right and to the left. In our first equilibrium problem, we're going to be able to tell that this system is at equilibrium by visualizing, instead of one arrow, we have the double arrows. So we've got a system that's going to reach chemical equilibrium. In this problem, we are provided with equilibrium conditions. We are provided with concentrations in molarity. The brackets stand for molarity here. If you recall, that is moles per liter, units of moles per liter. So we're going to have equilibrium values here from the rate of the forward equals the rate of the reverse. And if you take these equilibrium values and you plug them into what is called a mass action expression, you can calculate what is called an equilibrium constant. Down at the bottom, we're going to call that Kc. Equilibrium constants give you information about the chemical equilibrium system. If your K value is less than 1, this means that equilibrium is going to favor the reactant side. That is, at equilibrium, when the rate of the forward equals the rate of the reverse. If your Kc is less than 1, this means at equilibrium, it favors the reactant side. You have more reactants, less products. On the reverse, if you actually have a K value greater than 1, this means that equilibrium favors the product side. That at equilibrium, when the rate of the forward equals the rate of the reverse, that it favors the product side. So what we'd like to do here is calculate our equilibrium constant, and to calculate an equilibrium constant, you have to plug in equilibrium values. This problem gives us equilibrium values. That's why we're going to call it a level 1 problem. So to solve this problem, we're going to place the information that is provided into what I like to refer to as an equilibrium chart. In our equilibrium chart, it provides you with where you can place initial conditions. No initial conditions are given in a level 1 problem. But if they were provided, they would go in this section of the chart where it is labeled initial conditions. The only thing that was provided for this particular problem were equilibrium values, so we're going to plug them in where it says equilibrium. If initial values were provided, then we would be able to complete the chart and show how you could go from what you start with initially to what you're going to end with at equilibrium by going through some type of change. But once you have your equilibrium values and you're ready to calculate your equilibrium constant or do some other type calculation, you have to plug in your equilibrium values into your mass action expression. A mass action expression is nothing more than the ratio of the molarities raised to certain powers. And when you do so, you're always going to plug in equilibrium values into this mass action, and it's always a ratio of products to reactants. So in this case, we take a look at our chemical equation, and the first thing I want you to notice is that anything that's going to be included in the mass action must be in the correct state. Notice that my reactant here, the SO2, is in the gaseous state. The oxygen is in the gaseous state, and so is the SO3. Anything that's not in the gaseous state cannot be included down below in the mass action. If it's a liquid or if it's a solid, then we're not going to include it down below. But anything that's in the gaseous state, we will include it. Products always go on top. If you recall, we've already mentioned that the brackets stand for molarity, moles per liter. And the next thing I'd like for you to take a look at, that a lot of times students forget when they first start doing equilibrium problems, is that the coefficients that balance the equation, in this case the 2 in front of the SO3, notice it becomes the exponent down here in the mass action. And if you go over here and look at the reactant side, the SO2, it also has a 2 in front of it. And if we notice, it also becomes an exponent down below in the mass action. So anytime you have anything other than 1 in the balance equation, you need to remember to place it down in your mass action. It becomes an exponent. Now what we need to do is plug in the information provided for this particular problem. If you recall, it was all equilibrium values, a level 1 type problem. So we're going to take our equilibrium values and place them where they go. The 0.15 is the equilibrium for the SO3, so we can put it on the top part of the mass action. The oxygen we're going to place down below, that is one of our reactants. And the 0.75 we're going to place down below as well. So it's always products over reactants. Once you plug in your values, we can now calculate our equilibrium constant, our Kc value. In this case, our Kc value is less than 1. So this simply means that at equilibrium, when the rate of the forward equals the rate of reverse, that it actually favors the reactant side ever so slightly. Second problem that we're going to look at is also a level 1 problem. How do we notice that it's level 1? Well, once again, all equilibrium conditions are provided. Notice in this case that they have provided us with the Kc, with the equilibrium constant, and they would like to know the equilibrium condition for one of the products, for the Cl2 in this case. So once again, no initial conditions are provided, nothing is stated in the problem, it's all equilibrium values. So all we have to do is plug in what we know into our mass action and solve for what we do not know. In this case, that is the molarity of one of the products, the Cl2. So in our chart, what we have are equilibrium values. We don't have to worry about the initial conditions. They were not provided. So we simply plug in what we know. And the x is going to be our unknown. So we're going to plug that in for the Cl2. The 0.78 is going to go on the top part of the mass action. It's always products over reactants. All the coefficients in this balance equation are all 1. So we don't have to worry about raising anything to a power. And the 0.015 was the concentration of our reactant. And you may recall that this value happened to be given. It was 35. So we have everything that we need except for the unknown concentration of the Cl2. And algebraically we can cross multiply and solve for x. So the math will look like this. Once again, you can place the 35 over 1, and we can cross multiply, and you should be able to end up with the final concentration of the Cl2. The next type problem that we can look at is a level 2 problem. In a level 2 problem, they provide you with at least one initial condition and at least one equilibrium value. So we no longer have all equilibrium conditions provided. Here you're going to be given at least one initial value. So a level 2 type problem is where you have an initial value provided and an equilibrium value. Notice that the quantities here that are provided are no longer given in molarity, it's given in moles. And the size of the container is provided in liters. If you recall, to plug things into a mass action, you need it in molarity, moles per liter. So we're going to set up our chart. The one initial value that was provided was for the reactant, the N2O4. The one equilibrium value that was provided was for the product, the NO2. Notice I've placed the quantity, how many moles were provided, divided by the size of the container, in this case 5 liters. And once we divide these, we'll be able to get the concentration in molarity. And if you recall, those brackets down there in the mass action actually stand for moles per liter. So we go ahead and divide the quantity, the moles, by the size of the container, the 5 liters. We'll have our initial value provided in molarity, and our one equilibrium value also provided in molarity. Now we've got to complete this chart, because if we're trying to calculate our equilibrium constant, and we have our mass action expression below, we have to plug equilibrium values into the mass action for the NO2 and for the N2O4. Now we have the equilibrium value for the NO2, but at this point the equilibrium value for the N2O4, it's unknown. So we're going to have to find out what that equilibrium value is if we're going to calculate our equilibrium constant, Kc. So in a level 2 problem, if one initial value is provided, and they don't say anything else about the concentrations of anything else that is provided in the balance equation, then you have to assume that you didn't have any. You have to assume that it is 0. You have to make this assumption. So if they give you one initial value and they don't say anything else about the other initial value, you have to assume that you didn't have any. Now, how do you go from having nothing initially in this problem to having 0.2 at equilibrium? Common sense is going to kick in here and say, well, if I didn't have anything to begin with, and when my system reaches equilibrium, when the rate of the forward equals the rate of reverse, if I have 0.2, well, the obvious thing that had to happen here is I had to add 0.2. That's the change. How do you go from having nothing to having 0.2? You've got to add 0.2. I like to separate my reactants from my products with a dashed line that you see separating the reactants and products here. I'll emphasize it for you. Here's that dashed line. And I like to emphasize this because if you're adding on one side of the double arrows, you better make sure that you're subtracting on the other. That is, you cannot create something out of nothing. If you're adding on the product side, you better be taking away on the reactant side. Now the question is, how much are we going to take away? Well, we're adding 0.2, so at first glance you might think, hey, let me subtract 0.2 on the reactant side. However, you've got to focus your attention on the coefficients. If you recall, if nothing is written, there's an understood 1 for a coefficient. So what we need to do is take the change value, in this case 0.2, focus our attention on the coefficients. I'm going to take this 0.2 and I'm going to multiply it by the coefficient of where I'm going, in this case a 1, and divide it by the coefficient of where I started, in this case a 2. So in essence, I'm going to multiply this 0.2 change by 1/2. So half of 0.2 says that we're going to subtract 0.1. So how did we know to subtract 0.1? We focused our attention on those coefficients. That is, in essence, I multiplied this 0.2 by 1/2. Where did the 1 come from? From that balanced chemical equation. Where did the 2 come from? From that balanced chemical equation. So if you multiply 0.2 by the 1/2, that's how you get that you're going to subtract 0.1. So we go ahead and subtract it, the 0.2 minus the 0.1. We'll have our values at equilibrium. And now we can plug them into our mass action and calculate our equilibrium constant. Calculate Kc. We're going to plug in our 0.2 here. We're going to plug in our 0.1 here. Let's don't forget that the coefficient helps us balance the equation. The 2 in this case did become an exponent. Students like to forget this simple fact when they first